Your computer?
She's going to connect her computer. I'm the chair of the session, but our speaker is Katie, so she's going to connect her computer.
Okay. Hello.
Ladies and gentlemen, good afternoon. Can you hear me? Yeah. It's my honor to welcome you all to the Women Engineering session at ICCE 2025. This is the platform to serve as a collective effort of the engineering scientists who are dedicated to fostering the diversity and inclusion in our field. And I'm thrilled to see such a vibrant and engaging audience here today. So it is my great pleasure that I introduce our guest speaker, Katie Hayashi. Katie has been involved in the semiconductor industry in her entire career, developing and deploying and analyzing advanced software tools used to create the computer and mobile phone chips. At Unisys, she was on the team that created one of the first spray mainframe on the chip using the custom software. She has since worked at Cadence Design and System, which is the local startup, and then in Qualcomm, where she worked with the semiconductor workflow in the large scale compute environment. She's currently served as the IEEE Director of the Region 6 and a member of IEEE Board of Directors. She is also the senior member of IEEE and IEEE Honor Society. So for today, she will be sharing her insight on existing career opportunity in the semiconductor industry. So in this talk, she delved into cutting-edge research, practical application, and transformative trends that are defining the future of this technology. So Katie's journey and her vision will inspire us to explore how we can contribute to this transformative field too. Please join me to welcome Katie Hayashi.
Thank you. Thank you so much. I appreciate the introduction. And thank you, the IEEE Women Engineering, for inviting me here today. I'm very honored to be a part of this conference. So what we're going to be talking about just for a little bit here is about what's going on in the world of semiconductors. And I'll talk about the careers in semiconductors, but there's been a lot of change in this whole area. And I'll talk about some of the things and why there's a change, what opportunities are in semiconductors right now. And I'm hoping that we can have a little bit of discussion at the end. So I will not take up the whole time. I'll see if there's any Q&A before we head out to lunch. So as you heard in my background, I've spent my entire career in working in semiconductors. For those that are in the field, I do the front, or actually I do pre-silicon. My background is CAD, electronic design automation, or EDA. And I've written a lot of software, a lot of custom software, including some original hardware description languages, synthesis tools, timing analysis tools, and some that are currently in production in other EDA vendors. So I've had a long background in semiconductors, and I want to tell you a little bit about how things are changing and what's going on in that world. So as part of being here, we all know that electronic devices, and it's been all around in many topics of discussion here today. And you know that in almost from the time that we start in the morning to the time that we're going to bed, we are using electronic devices that use semiconductors throughout the entire day. And so some of the things that happened, especially during the pandemic, was that we were unable to get some of these chips out to market. And I was actually working at a fabless company during that time, and we definitely didn't have the resiliency that we needed in the semiconductor workflow at that time. And as people were trying to get the chips, many people in the industry, including myself, we were working to respin a lot of designs to get them to other fabs so that we could actually keep the resiliency within the semiconductor industry. So I had designs that were at one fab, and I was spinning them as fast as I could, which is not easy, to get them out so that they could work with another fab. And that's what we were doing to try to get the resiliency. But overall within the industry, we're looking for how we can make even more resiliency within this industry, because it is so important for us, and that we want to make sure that we always have these devices available. So where are semiconductors being used? And here's just some of the industries in the verticals. Now, if you were at CES, you saw a lot of the automotive, but it's also used a lot in communications, many of which IEEE has conferences dedicated specifically towards them, including this one as well. Now, for those in the semiconductor industry, you know that a lot of things that we look at are making sure that we are monitoring the power, how much is being used by the semiconductor devices, the performance, is it speedy enough, and in the area, do we have it in the right form factor for what you need? Now, I'll talk a little bit about the differences in the industries of what they need in terms of power, performance, and area, but those are some of the things that we look at. And here's some of the industries that the semiconductor chips in terms of overall magnitude. Now, some of the things like you see the government, they have small volume, but they have a lot of requirements. And those on the left, they often have high volume, like the communications in your phone, high volume and also stringent requirements. And it's trying to make sure that we can make chips across all of them because they're all important. So if you have high volume, we want to make sure you get your chips out, but if there's low volume, we also want to make sure that there's chips. So that's some of the things that we are trying to work towards in terms of resiliency and robustness, is making sure that no matter what your volume is, can you still get the chips out, and can you get them out with the resiliency and robustness that you need? Now, again, if you were at CES, you saw some of the cars and the automobiles. Right now, these cars have hundreds of chips in them. And just in the panel before, they were talking about functional safety. There's a lot of FUSA things and standards that are going into a lot of these chips, so that to make sure that if you are down the highway and something happens, one of your chips overheats, we want to make sure that it has a second pathway and that it will get you, it may be degraded, but it'll be able to get you over to the side of the road as safely as possible. So within these, you can see that there's a lot of chips. And if we're talking about resiliency, we need a lot of people and a lot of large ecosystem to make sure that we can make and continue to make these, even if something happens to our supply chain. Now, another one is in terms of communication. There was also sometimes we couldn't get the chips that were in some of the mobile phones. Now, many of you are very much aware of Moore's Law. And my perspective of Moore's Law is I was actually writing software to help the engineers get to each one of these process nodes. And so I would write EDA software that took it from what you're seeing on one end there is the very large phones. And each time and every year as part of Moore's Law, we were trying to make them smaller. We were using less form factors, so we're making smaller, but put more logic on them, more gates. And then also another requirement was to make them cheaper than they were before. And so then as you can see that these phones, which are big, they're starting to get smaller. And they're also having more functionality. You see that as some of your phones have much more functionality than the ones that we had way back then. And then also they are using more efficient use of batteries, because we even have multiple things that if you have high battery, it'll do some things, low batteries, it'll do other things. So there's a lot of interesting techniques that can be used in order to make sure that a lot of things happen. So with Moore's Law, that was, we were able to do a lot of in making sure that we're moving the technology forward. And when we were doing that, it has always been a global ecosystem. And what I mean by that is that we would actually design in one location around the world, and then we may have verification done somewhere else. We could do this fab will be in another location, testing somewhere else, and then actually assembly and other things, and the customers worldwide. And so with that, even today, we still have a global ecosystem, and we will continue to have that, but we're going to do more in terms of resiliency and robustness, and making sure that we're able to not just pick the latest in technology, but have a little bit more business sense and savvy to the way that we're making computer chips. I can definitely say that we were very technology focused, and Moore's Law made us we were very focused on the technology, hitting the markets, but now we've got to have another factor that we need to consider. So not only is it power, it's performance, it's area and resilience and robustness, and of course the other things of security and other things that we need to make sure that we're putting into our overall design flow. Now, because of this, there have been initiatives around the world related to increasing the supply chain for semiconductors around the world. So many of you might have heard the United States CHIPS Act, right? So that has put in a large infusion of money and interest on improving the semiconductor value chain within the United States. But there's also the European CHIPS Act. There's also things in Asia, in Japan and India and many other locations, and also a lot going on in Latin America. So it is around the world that everyone understood that this supply chain needs to go global. And so one of the things is what I've been working on the last 2 years is helping people understand, what does it mean when you say semiconductor value chain? What does it mean? And trying to understand how that will help and be used by all the different areas around the world. It was often thought that when we first started the discussion, everyone thought that semiconductors equals fab. Oh, we need to have more fabs. But as you can see from this one, this was taken from the National Economic Roadmap coming out of Arizona. There's R&D, there's research and development that occurs. There's also IP. There's design, where the engineers are working on the chip. This is all pre-silicon, before the fab. Then you've got to have materials and understanding what goes into semiconductors, and that is changing a lot. They're using a lot of different new materials inside the fabs. And then, the equipment, the robotics, and then over here, the column, that is actually the fab. But you can see there's so much before you put something in the fab, and there's a lot of things after the fab. And so there's package, assembly, and test. And then, also distributing as well. So within each one, not only are there many areas of the semiconductor value chain, but then also we need infrastructure, we need supply chain, workforce, and also there's a large focus right now on entrepreneurship in this overall area. So there is, in terms of going back to careers in semiconductors, there is a lot here, and it's not just semiconductor fabs. It's those people that can do all of this, which is a quite large amount of resources needed to do a lot of things to make a computer chip. And as an example, if you're doing a large system on a chip, for, maybe for a mobile communications device, you could have thousands of people working on that chip. That's just thousands for one chip. And imagine if you're in the car and you're seeing hundreds of those. That's a lot of people that are required to make a computer chip. So part of this is what they found over time, is that there's going to be, if you want to provide resilience and robustness within the semiconductor industry, they're projecting by 2030 that we're going to need hundreds of thousands of jobs just in the United States alone. And that's not including all the other areas around the world that I discussed. And if we go at the current rate that we are having people interested in the semiconductor field, and people like myself, there's 60% of those jobs are going to go unfilled unless we do something. And so this is from an article by the Semiconductor Industry Association, SIA, and they kind of broke that down, that if you have more fabs and more parts of the supply chain, that you're going to need around 40% more technicians in order to put those fabs in there. And these are in areas where there were not fabs before. So you need to get that talent and get that industry there. In addition, you'll need 35% computer scientists and engineers to help run. Remember I said there was the stuff before, making the chips and the things that go into the fab and the things that go after the fab. And then you also still need your advanced skilled workforce, and that's your advanced degrees in engineers. And that is the same, but you'll need more of them because now we have more fabs, we've got more resources, and there's a lot of things that we need for the workforce. So there's a lot of things going on in semiconductors. We're going to need a lot more people. Now this is actually from an IEEE publication that's put out by Tri-Engineering in Semiconductors, but it's a really good diagram of all the different careers that you have in semiconductors. Now for mine, I am more at the front end for software, writing the software that helps make the computer chips, but we also need everything from taking that software, we have people that need design, and if you even go back a little bit, we need people that understand the market, that they understand how, what are we going to be building 5 years from now? What do we need to be, working towards? So we need people in marketing. I need people that are program managers. I need infrastructure and IT. We need CAD softwares. I need, people that are interested in statistics and artificial intelligence so that they can use the data to improve our processes. And then also, we need engineers, people that understand the physics of the different chemicals and resources used in the fab. And so with each area, there's so many areas within semiconductors. It is a very diverse environment that needs a lot of people working together around the world to make things happen. So to address the challenge, around the world, people are working to build the supply of engineers and scientists. We need to take new approaches to the way that we're bringing people in. For example, if we're looking at more skills-based rather than degree-based. So if you are working in the fabs, we want to make sure that we have like micro-credentials or certificates that will get you into the fabs areas. And then also making sure that if we are having people get these degrees, that there is the ability to go straight from universities to industry, and that these things are directly applicable to it. And, of course, expanding the pipeline. And to do that in the talent pipeline, we have to think about all the way back to pre-career. And one of the focuses that we have is focusing on those that are in like 8th grade and above, because if you are not aware of the word semiconductors, that you too can make computer chips early, that is something that when you're looking for careers, you may not choose. So we have several different programs focusing just even people introducing what is semiconductors, what does it mean to create a chip, is it something that you can do? And then we have, once you are getting these degrees, having vocational training, having those micro-credentials, and then also the traditional four-year college and advanced degrees, but also bringing prototype fabs and other things so that we can merge the university and industries working together on things, so that when we have someone that's in the university, I want you to be able to tape out and then create your chip, and then be able to actually see your chip and use it while you're still in school or while you're still developing it. And then when you go to industry, you will know very well how to make a computer chip, and you'll be well on your way. Also, for those that are like myself, we've got the senior careers, making sure that we have a lot of knowledge on how we've made chips over the years, and if we can help expedite or get people into these pipelines even more. So we want to make sure that we're covering the talent pipeline from beginning to end. I just wanted to quickly bring up, there's two publications from IEEE right now. One is from HKN, the Honor Society. They have the bridge, and it has many articles related to semiconductor resiliency. So you might want to take a look at that, especially if you're in IEEE and you want to know what IEEE is doing relative to the semiconductors. There's a wealth of knowledge because IEEE and semiconductors, there's so much going on and so much synergy. The bridge has a good article on that. And in addition, the Tri-Engineering, A Journey into the World of Semiconductors, is very high level, but I have used it many times for those people that are just starting to get into semiconductors. And it's like, well, what is a chip? Well, that's the question that's asked on the second page of this article, or this pamphlet here. I've been involved in semiconductors my entire career. It is something that I would not change for anything. I have been able to make an impact. I've worked on things that have never been done before, and I've worked on things that I had no idea that it was going to have the impact that it did. And I hope for those that are interested in semiconductors that you might consider this a career, or if there are other people that you know that might be interested in them, that you help lead them to careers in semiconductors. Thank you.
Oh, thank you, Katie. So we actually have a few minutes, Kathy, I'm sorry. We have a few minutes before we actually break for lunch. And so there's an opportunity for some questions or comments. If somebody would like to, Wahab.
Thank you very much, Kathy. Thank you, Mirzia. With regard to the semiconductor value chain that you said it is distributed worldwide, you do the testing in Brazil, verification in Europe, design in North America, etc., etc. So how did you manage this during the COVID time? How did you manage this during the COVID time? Because we have a shortage of semiconductors during the COVID time.
So during the pandemic, you may have noticed that chips were hard to get. So for those of us that were making computer chips, like sometimes where we were getting a particular item in the supply chain wasn't able to deliver. And so within the industries, what we were doing is we were looking for, okay, we can't get this particular functionality here, so we're going to go and we're going to, what we call respin, we're going to go somewhere else and see if we can get it there. We were trying all different avenues of existing things within it. So for example, there was one fab that was totally full and backed up. So I took a design with a bunch of other people, and we did some things so that it would be able to be manufactured at another fab. And that's a big deal, and that's hard to do, but we needed to do it because we needed to get those chips out to market. So in the industry, it says we re-spend on a different process node for a different fab. And so that's things that we were doing inside the industry. Now, when it's all said and done, after we've done that and we're exhausted, we were saying, okay, we need more resiliency. So now we have to find more fabs, more options, more second sources and things like that. So yes, during the pandemic, everyone was working to do the best they could to get some of these designs out there. But then after it was done, we need more resiliency. We need more, more global interaction on the supply chain. So.
Over here.
Yeah.
Kathy, I enjoyed your talk. My name is Mustafa. I'm based in Germany, professor of microelectronics. I'm also the founder of a small fabless design house in Germany. I completely know your pain. It's very difficult to find talented young people to work in chip design, especially young ladies. And I think academia does its part, but also I'd like to make let's say a plea for the industry to contribute. We have an outreach program where we actually teach fresh graduates who just studied electronics, who may know how to do a tape out but don't really know what it takes to be a designer for products, how to become an actual designer for products and for industry. So I think if small companies like ours can do that, big institutions can also contribute. Thank you.
Well, thank you for that, and I am fully supportive of that. For those who may not know, I've been the Women Engineering Leadership Conference. I was chair for 2 years, again, trying to get more people to be comfortable within the semiconductor space, and I will continue to help with that. But yes, there's many things, there's many differences between what goes on in the universities, which are doing a great job of getting them in, and it's our job in industry to keep them in. And, there's a lot of studies, a lot of statistics. We don't need to go into that now, but industry can do more to keep them in and keep them in longer. And part of that is helping that, you're going to be scaling larger than you've ever imagined with when you're in industry. We're going to do things that need to be more defined and repeatable. We're going to do some challenges, doing some things that, have never been done before, but by the way, you got to have it done by October. And so that is where we can really help, working together, get more diversity in semiconductors by, by meeting, and by really encouraging other and finding ways to really support us in industry. Tom.
Hi, Kathy.
Hi.
Oops, sorry. So I know one of the things that the committee has done is they've worked with SEMI in developing training classes for technicians and other people who are going to work in these facilities. Are those available outside the United States? And if so, considering where people are from, how can people access things like that IEEE has done to help?
Well, I have a whole slide deck on the other side, which that talks just about. It talks just about. I assume you're referring to micro-credentials and other things. Okay, so it's in those articles that I referred to, but IEEE is doing quite a bit to help support semiconductors around the world. So one of those is the micro-credentials, and the micro-credential program is providing skills-based certificates or micro-credential certificates. And people around the world, if you're interested in learning about those, several people are offering them up on the IEEE site. And then also on the previous one I said, Try Engineering / Semiconductors, there's videos on there that you can go to right now that tell you what is packaging and getting started on other areas in semiconductors, and on, let me see if I can find this one. So many things. There, on the global semiconductors. And Kathy Grice, are you still here? Yeah. She is our staff, and she is helping us with the IEEE Global Semiconductors Initiative. And if you go to this website, semiconductors.ieee.org, we have tried to aggregate, working with educational activities and other groups, and tab groups, to aggregate all of the training within IEEE so that people have a one-stop portal that they can go directly to those sites. So within IEEE, there's an immense amount of content, and IEEE Global Semiconductors, we're trying to get it in a form that other people can use to connect IEEE with the Global Semiconductor Initiatives that we talked about earlier, and have the Global Semiconductor Initiatives also reach out to our members as well. Are there other things you wanted to add, Tom, or did that, okay? Yeah.
Oh, so yeah, maybe other questions here, but maybe I'll throw one in. Oh, I'm sorry. Go ahead.
Have a follow-up question. Being in the male-dominant industry, I want to get your some of your experience that how during your career you keep yourself motivated to be overcoming all the barrier and get a leadership opportunity in this predominantly male dominated industry.
Well, with that, anytime there's diversity, there's a couple of strategies that we can take. And one of them, I'll give a shout out to IEEE, that IEEE allows for networking opportunities. And with that, you're able to talk to people in the industries that you're from and be able to get some strategies and talk with them about how to approach things, and also getting some additional opportunities with that. So one is that if you're currently in those environments and you need some support either on how to handle situations or how best to move forward in your careers, that is the networking. That's what's happening here. That's what IEEE is really good for. But those are some of the strategies, is to get mentors, to get people, if you're having situations, have that, mentors or networking that you can talk to people about. And if you're looking for the opportunities, look to see where you can find additional opportunities above and beyond what you're doing in your job. So, for example, you can sit there every day and you can just go and you can, write code and go home, write code and go home. Or you could go to a conference and talk to some of the industry leaders and learn more about how your code fits in with everything else. The second part is, how do we actually move the needle? How do we make that change? Well, part of that was that if we are getting more people involved in the industry earlier on, the magic number that we need is 20%. So if we can get people that, have diversity, get them from universities, get them into industry safely, and to have them being productive inside industry market, that is what we need, we need more people in there. And part of these global semiconductor initiatives, especially, I've been involved in 3 workforce development proposals so far, and each and every one of them had a paragraph on how we're going to make this more diverse. So do we need more opportunities for daycare? Do we need more opportunities to work from home? People are talking it, and people are trying to figure it out, and let's be part of that solution to try to get diversity of all kinds inside these programs.
I guess we are coming to the end of this session, but maybe I can squeeze a question in as well. I was kind of intrigued where you showed one of the slides talking about maybe getting people engaged as early as maybe 8th grade in this industry. And over the course of my career, even though I haven't focused on this, I've seen things like the Carver-Mead method, which have somewhat democratized the ability for people, even at the high school level, to do chip design and that sort of thing. But to go from the design to an actual functional working chip, there's limitations on that. I know there have been some fabs that have allowed you to do something less than an entire wafer using direct e-beam right, and you can get some stuff back. But we had some earlier discussions today about digital twins, and it just occurs to me, is there an opportunity to take some of these high-level languages where it designed the chip, and instead of having that barrier to actually get the physical chip in hand, to use a digital twin where we can give the 8th grader, something that actually appears to be a working chip? Is that something that's on the, or is there some other way to kind of take it from the high school and, to actually giving them a little satisfaction more than just seeing the design on the computer?
Yes, well, it's a great question and great points. There's 2 parts to that, actually. One is we talk about digital twins, and definitely in fabs, everyone's talking about digital twins in the fab, so that you have what is going to be created in the fab, and then also the digital twin. That allows you to get a little bit sooner time to market, process and characterization, and those sort of things. So it's definitely talked about in the fabs. Pre-silicon, pre-design, we're kind of looking at it funny because we've been using hardware emulators for quite a while. And so what it is, it's a hardware emulation of the chip itself. So when I'm working on a chip, I have a hardware emulator that is actually emulating what the chip is going to be doing. And so that is how we get system integration and how we can get chips out every year. So yes, definitely digital twins has a big part, or at least being able to simulate and emulate is a big part of semiconductors. Now, the second part of the question was, how do we get everyone to tape out? So one of the things that I did just a couple months ago is we had a session just about like this, and within 3 to 4 hours, we had everybody taping out on something called Tiny Tape Out. Because one of the things that I did at the beginning of the session is I had a whole bunch of people that were in the semiconductor either going for university or interested in it. And I said, how many people, are in semiconductors? Everybody raised their hand. And I said, how many people know what a tape out is? And only 5 people raised their hands. Tape outs are huge. Tape outs are when we have the design and we give it to the fab. We had over 100 students tape out in one day. And this is at Tiny Tape Out, where they have pretty much like a test chip. It's one chip, but it's got a lot of different designs in it. And that is the way that you can get, hundreds at a time making computer chips. So it's real. It's something that you can actually take. It'll be manufactured. Delta time to manufacture and return is about 6 months, a little bit too long, but it allows you to create computer chips, and that should be accessible. And it's accessible, why? Because some fabs allowed us to have PDKs that we could actually open source for some things. And second is that we have programs like this where we're putting multiple designs on one chip that allows us to manufacture at a reasonable cost. And then if we have people such as that provide grants, and this one was within a grant from UCSD and sponsoring by IEEE Region 6, we were able to get 100+ tape outs on their last die. So yes, and I've also talked to IEEE Tri-Engineering. Can we also do this more? And I know that a lot of societies have done this. I know that in the Latin America, there's some programs from IEEE doing this. Let's do it even more, and let's make even more people have tape outs. So.
For some what?
So I don't know if I can have a very quick question. By the advancement in the AI and machine learning, how do you see the change of semiconductor industry in the next 5 or 10 years?
So I'm actually been in the industry a long time, and I used AI-based techniques back in the day when I was doing synthesis and a lot of layout and routing and those sort of things. So AI has been a part of semiconductors for a very long time. In fact, we were doing neural nets many, many, many years ago, and we determined that we didn't have enough compute power and we didn't have enough data. And then within the last 10 years, look at that. We've got enough compute power with the GPUs. We have more data than what we know what to do. And in almost every semiconductor tool we've ever written, they're now using AI techniques, and they always have and they always will. With that, what I did back when you saw that Moore's Law took me a year, right? That's what Moore's Law is, 1 year to 2 years to get to every process node. That can pretty much be done now today. They're touting 24 hours, but I do know that everything that we did is now automated. And then part of that is because we know and we told them how, or we were writing tools that now do what we did. Am I scared? Am I like out of a job? No, we've moved on. Now we've got hybrid, we've got packaging, we've got advanced packaging, we have new resources that we're using, we've got more chips than we know what to do with, we've got other things. We're moving up the stack. I always remember at a design automation conference back in the day, there was a whole article written about how the tools that we were writing. So I write custom design automation tools. And there was an article written that's like, wow, this is going to put everybody out of a job. And we didn't do it then, and we're not going to do it now. In the design automation, yes, I wrote a lot of tools so that they don't have to use the light tables and they don't have to use the templates and the pencils and the rulers. But now they had to use the computers, and the schematic part was a lot easier, but now I've got big other problems for them to worry about and other things that they needed to do. The global semiconductors on a chip being used around the world. And all those people that I taught them how to use my tools, and they were so excited because now they can do it even faster, and they could go even farther and get things done a little bit better. So I'm still excited about the industry. Thank you.
I can't wait to think about going back to 8th grade. I'm very jealous I be able to do this. So I think we've come to the end of the session. Let's give Kathy a big hand and thank her so much. So I'm told that Stefan, you want to make some announcements? Yeah. And so a couple more announcements and then we'll break for lunch.
So much.
Thank you, Kathy, for your inspiring talk, and thanks for the audience for their great question and engaging one. Thank you, and enjoy the rest of the conference.